Hello friends, welcome to online lecture series. This is the sixth lecture of your unit number 1, that is wave mechanics. So in our previous 5 videos, we discussed what is operators and different types of operators. Okay, so this is the second theory of your unit number 1, that is particle in one-dimensional box. Okay, so this is the second theory of your unit number 1, that is a particle in one-dimensional box. So subtopics of particle and one-dimensional box. First one is Schrödinger equation. Second one is a wave function. Third one is energy and energy level. And last one is normalization and orthogonal condition. Normalization and orthogonal condition in one-dimensional box. Okay, so these are the subtopics of particle in one-dimensional box. First one is Schrödinger equation for particle in one-dimensional box. Second one is wave function for particle in one-dimensional box. Third one is energy and different energy levels in one-dimensional box. And last one is normalization and orthogonality condition in a one-dimensional box. Okay, so these subtopics are common in our next theory, that is a particle in three-dimensional box. These subtopics are common in particle in one-dimensional as well as particle in three-dimensional box. Okay, so now first one is what is the equation of Hamiltonian operator. Hamiltonian operator we discussed in our lecture number 4. Lecture number 4 contain two types of operator. First one is Hamiltonian and second one is momentum operator. Okay, so now first Hamiltonian operator. This is the basic introduction. Hamiltonian operator. What do you mean by Hamiltonian operator? Hamiltonian operator indicates the total energy of any system. Hamiltonian operator is denoted by H cap. It indicates the total energy of any system. It means one-dimensional, three-dimensional, rectangular, two-dimensional. Okay, if any box, if in any system, Hamiltonian operator indicates the total energy of this system. Now total energy, it means it is the sum of two types of energy. First one is kinetic energy plus second one is potential energy. Hamiltonian operator indicates total energy of this system. Total energy is sum of two types of energy, kinetic plus potential energy. Okay, so for one-dimensional box, what do you mean by one-dimensional box? One-dimensional box, it means suppose any moving particle is linear motion in any one direction. It means suppose I assume this particle is moving from here to here in only x-axis, is along to only x-axis. Okay, so another parameter, that is y-axis and z-axis, is not considered in this case. One dimensional means your particle is moving along to only one axis. Suppose that axis is x-axis. Okay, so what is the equation of Hamiltonian operator in last lecture number 4? What is the general equation of Hamiltonian operator? H cap is equal to minus a square upon 8 pi square m del square plus capital V. This is the general equation of Hamiltonian operator. This term indicates First term minus a square upon 8 pi square m del square indicates kinetic energy. And second one is capital V indicates this is the potential energy. Okay. So what is the value of del square? Del square is equal to del square upon del x square plus del square upon del y square plus del square upon del z square. Okay. This is the capital del and this is the small del. Both are called del. Okay. So the value, it is a Laplacian operator. It is a Laplacian operator. And capital H is a Hamiltonian operator. It is all Laplacian or del square. It is called Laplacian operator or del square operator. Okay. So in this case, our particle is moving along to x direction. It means only variable x is considered. At that time, variable y and variable z is not considered. Okay. So the value of del square is equal to del square upon only del x square. These two terms are not considered in one dimensional box. Okay. So if our particle is moving along in 3 dimensions, it means x axis, y axis and z axis. 3 axes are considered. At that time the value of del square is equal to del square upon del x square plus del square upon del y square plus del square upon del z square. Okay. So for one dimensional box, Hamiltonian operator can be written as, for one dimension, for one dimensional Hamiltonian operator can be written as h cap is equal to minus a square upon 8 pi square m. Now the value of del square is equal to del square upon del x square plus capital V. Okay. This term indicates the value of kinetic energy and capital V is potential energy. And Hamiltonian operator in 3 dimensions. For 3 dimension, Hamiltonian operator can be written as, if your particle is moving in cube, like cube is a 3 dimension. Okay. At that time x axis, y axis as well as z axis, 3 axis, all the 3 axes are considered. It means the value of del square is equal to del square del x square plus del square del y square plus del square del z square. Okay. So in this case, Hamiltonian operator can be written as minus h square upon 8 pi square m into del square upon del x square plus del square upon del y square plus del square upon del z square plus capital V. This is kinetic energy and that one is potential energy. Okay. So this is the basic introduction of Hamiltonian operator. So in our next theories, it is the most important operator. It is the most important operator in our next theory. It used in many times. Okay. So for a one dimensional Hamiltonian operator, minus h square upon 8 pi square and del square upon del square plus capital V. Here the value of h cap. What do you mean by h cap? It indicates a Hamiltonian operator. Small h, it indicates a value of Planck constant, 8 pi 3.14 m. M is the mass of the particle. Del square upon del x square, it is the mathematical procedure. And capital V indicates potential energy. Okay. So this is the basic introduction of Hamiltonian operator. Our theory is not start from here. Okay, this is the basic introduction of Hamiltonian operator, because this operator is used many times in our next theories. So you should have knowledge about what Hamiltonian operator in 1D and 3D. Okay. So first topic of particle in one dimensional box is Schrodinger equation. Schrodinger equation in particle in one dimensional box. So I will derive Schrodinger equation in one dimensional box. Okay, suppose any particle which is free to move in space belongs to x-axis. Suppose any particle which is free to move belongs to x-axis. Okay, so here the value of x is equal to 0 and the value of here is suppose x is equal to a. Okay, and these two are imaginary wall. This line indicates imaginary wall. Okay, so consider a particle. Consider a particle with mass small m, which is free to move along to x direction in absence of any field force. In absence of any field force. Okay, suppose consider a particle with mass small m. It is travel along to x direction, which is free to move along to x direction in absence of any field force. What do you mean by in absence of any field force? Suppose this is a chalk. Now I release the chalk, so it gives, so it pull to downside because earth gravitational force attracts these chalks towards itself. It indicates the presence of force, that is a gravitational force. That is a gravitational force. But in this case, no any field force are present. It means in absence of field force, there is no any field force like gravitational another extra field force are not taken in this case. Okay, so in absence of field force, the value of potential energy is constant, and we assume in this case the value of potential energy inside this boundary, inside this box is equal to 0, and outside this box potential energy will become infinite. Okay, so for in absence of field force, the value of potential energy is 0, and we assume the value of potential energy is equal to 0. So first Hamiltonian operator. First Hamiltonian operator for particle in one dimensional box. Okay, h cap is equal to minus h square upon 8 pi square m plus capital, this is minus h square upon 8 pi square m into del square upon del x square plus capital V. This is the equation number 1. Okay, so in one dimensional box only x axis is considered, so another variable y and z is equal to 0. Okay, so this is the equation number 1. It indicates the value of Hamiltonian operator, and first term is the value of kinetic energy, and second term indicates the value of potential energy. Okay, so for in this case, in absence of field force, between x is equal to 0 to x is equal to a, it means in absence of field force the value of potential energy is constant, and we assume the value of potential energy is 0 inside the box, but outside the box potential energy will become infinite. So in absence of any field force, the value of potential energy is constant and we assume it is 0. Okay. So in absence of any field force, the value of potential energy is constant and we assume the value of potential energy inside the box. It means between boundary condition, here the value of x is less than or equal 0 and less than or equal 1. Okay. So the value of x, in this case the value of x less than or is equal to 0 but less than is equal to 1. It means x is lying between 0 to a. Okay. So this is the value of x. X is lies between 0 to a. Okay. So in absence of field force, the value of potential energy we assume 0. It means in our equation 1 the value of v is equal to 0. So therefore Hamiltonian operator h cap is equal to minus a square upon 8 pi square m into del square upon del x square plus the value of potential energy is 0. So this term are not considered. This is the equation number 2. Okay. So for Schrodinger equation, we operate Hamiltonian operator in any function. For Schrodinger equation, operate Hamiltonian on function, that is psi. Okay. So the value of h cap psi is equal to e psi. The value of h cap indicates Hamiltonian operator. Psi is the function, a is called eigenvalue, but in this theory, particle in one-dimensional box, it indicates energy. It is called eigenvalue or energy, and psi is also function. Okay. So therefore the value of h cap is minus a square upon 8 pi square m, a square upon 8 pi square m into del square upon del x square into psi is equal to a into psi. Okay. So now here minus a square upon 8 pi square m is left hand side. If these terms are goes in right hand side, then it becomes inversely. It means a square is in numerator term, it will become denominator, and 8 pi square m is the denominator and it will become as a numerator. So the value of del square psi upon del x square, del square psi upon del x square is equal to here minus 8 pi square m upon h square minus 8 pi square m upon h square into e into psi. Okay. So this is the equation number. Here minus 8 pi square upon h square in e into psi is the right hand side. If these terms are in left hand side, then minus value will becomes plus. It means del square upon del x square plus 8 pi square m upon h square e into psi plus 8 pi square m upon h square E into psi is equal to 0. Okay, so this is the equation number 4. So this is the equation number 4. Del square psi upon del a square 8 pi square m upon l square a into psi is equal to 0. This equation indicates the Schrodinger equation in particle in one dimensional box. Okay, so this is the Schrodinger equation for particle in one dimensional box. So in our this theory, 8 is a constant. 8 is a constant. Pi, the value of pi is also constant. M it means mass of particle, but in absence of any field force, the mass does not change. Okay, so mass is also constant, energy constant, and h square is h. The value of h is Planck constant. This all terms are constant. 8 pi m e and h in only one dimensional box. So suppose these terms, suppose I assume all these terms are the value of 8 pi square m e sine upon h sine h square is equal to k square. Okay, here k is another constant. So equation number 4 will become del square psi upon del s square plus k square into psi is equal to 0. This is the equation number 5. Okay, del square psi upon del x square k square into psi is equal to 0. Okay, so equation number 4 and equation number 5 both are the equation of Schrodinger equation in particle in one dimensional box. So equation number 4 and 5 are equation of particle in one dimensional box. Okay, so the equation number 4, del square psi upon del a square plus 8 pi square m upon a square a into psi is equal to 0, and another equation is del square psi upon del a square plus k square into psi is equal to 0. These both equations are equation of particle in one dimensional box. Okay, so this is the first of topics of your theory particle in one dimension. The first topic is Schrodinger equation. So now another topic is wave function for particle in one dimensional box. So another topics of particle in one dimensional box is wave function. Okay, so in this theory I will discuss Schrodinger equation of particle in one dimensional box. So in our next theories I start wave function for particle in one dimensional box. So I hope you enjoy this lecture. So thank you for watching this video.